Hello everyone and a warm welcome to today's video where we will be going through some of the recent questions of the topic of course, radio navigation and more specifically about radar. So we will cover the primary radars, the weather radar and the transponders or the secondary surveillance radars. So without any further ado, let's go into the questions, explanations, and I'll try to give you some extra tips for the exams. So for question number 1, which of the following systems can report an aircraft's altitude to a precision of 25 feet? And this is a very standard question for radio navigation. So of course, the transponders are divided into 3 key categories that we need to know. Transponders Alpha, Charlie, and Sierra. Alpha is the most basic one. It only reports your transponder code. Then the Charlie is the slightly better version. Charlie also starts reporting some basic information, mainly the altitude at increments of 100 feet, and then lastly the Sierra transponders, which can report the altitude down to precision of 25 feet. And also the Sierra transponders are necessary for the arrays, so the resolution advisory when it comes to TCAS, and the Charlie transponders can also issue the traffic advisory when it comes to TCAS. So these are some of the most important bits to remember for these types of questions when it comes to transponders. Of course, this question, the only one that reports altitude to the increment of 25 feet will be A mode Sierra or S transponder. And this is a little bit of a wordplay here, so I can see how this can be confusing. However, of course, only Sierra reports to 25 feet, Charlie to 100, and alpha mode transponder doesn't report altitude at all. It only gives us your, or the controller, your transponder. And here also additional information. So in most cases, the controllers will see your aircraft on their screens and the information given by the transponders. Also, these days, because of the advanced ADS-B systems, the controllers can see not only your parameters, but also what you set on the autopilot panel, even if it's not active yet. So this is just a little additional information for you. For question number 2, a weather radar set to 100 nautical mile scale shows a squall line between 40 and 50 nautical miles. By changing the scale to 50 nautical miles, the returns on the radar screen should do what? And this is a very practical question. However, I know it might be hard to visualize it without seeing the actual navigation display and the weather radar. So I'll show you this in just a second exactly how it works. However, for questions like this, all you need to do is imagine a map. So what happens to houses and roads when you have a bigger scale and you decrease it? Of course, the houses, the roads, and everything on the map will enlarge because the scale is decreased. And exactly the same thing happens here. So of course the area will increase as you decrease the scale. And because now the area is increased, of course, it will move to the top of the screen as now the distance relative on your screen will be larger. However, as I just mentioned, it's best to see it. So I have an image right here. So this is something that happens on the right side. You can see we have, I believe this is 160 or 100 nautical miles range. On the left side, you can see we have a 40 nautical miles range. So the quality is not perfect. However, it allows us to see the entire principle. On the right side, you can see we have a very large scale, and we can see some of the cells and the returns. On the left side, however, the moment you decrease the scale, you can only see the 4 closest returns. However, they become a little bit bigger and they move slightly to the top of the screen because now the ranges are a little bit different. So you can see how this works when it comes to changing the range on your navigation display. And this is also a really important consideration. There is something called gain. So we can change a couple things when it comes to weather radar. These will be the range on your navigation display, will be the tilt, so where the antenna is pointing up or down, and the gain. So here you can see the exact same returns. And on the left side, we have an increased gain, a very sensitive radar. And on the right side, we have decreased gain, so less sensitive radar. I'll just mention very quickly that the gain is something that we can use in order to identify which cells are the strongest, because with the highest gain, highest sensitivity, we can only see red returns. When we decrease it slightly, you see which ones are the strongest. So this is something that we can do at lower altitudes. As you climb higher, it's always good to increase the gain because there are less and less stronger returns. So going into question number 3. What information may be displayed on an ATC radar screen connected only to a primary radar system? So the primary radar system is something a little bit different than the SSR, or the secondary surveillance system. The main difference is that the SSR is based on the principle of interrogate and response. So the radar will be sending an interrogating signal to a transponder, and then transponder in a slightly different frequency will send a response with all the given information. This is an SSR. A PSR, the primary surveillance radar, works on a very simple principle of deflection, or the echoes, where the radar is sending a signal and then the signal is reflected by anything in reality, and then it's collecting back the returns, and this gives mainly the range and bearing data for anyone who's viewing it. So of course the primary radar system only gives our aircraft's position, or as I mentioned, the range and bearing is everything that we see. Now with today's modern technology and transponders, besides the radar returns that are just bearing and range, we can also see the speed, the altitude, the call signs, but that is the job of an SSR. The primary radar systems give you only bearing and range, which is aircraft's position. And now for question number 4. So in the weather and turbulence mode, the airborne weather radar is able to detect. So here, just a little overview and summary of the weather radar on board of your aircraft. So the newest airliners will use a planar slotted array antenna for the weather radars, which will operate in the short frequency range. This is a relatively high frequency, definitely dangerous for humans. This is also one of the reasons why you will never turn on your weather radar when you're close to the apron or the area where the passengers or airport employees are working. We always turn them on once on the taxiway or away from people. The newest weather radars also can detect turbulence. However, they detect them on the principle of the pulse flattening, pulse shifting, or the Doppler effect. The Doppler effect is nothing else but detecting a movement of particles. So if the weather radar, because it's a primary radar, it sends a signal, then it decodes the deflection and tells us what we're looking at. If something is moving, like the cloud, the water droplets, or hail, in that case, the return will have a slightly shifted frequency. The newest computers in these aircraft are able to detect those shifts in frequency, and they can tell us where the turbulence, which is essentially movement of air, is expected to see. However, this needs some particles to be moving, and these particles in most cases, will be rain or wet hail. Some of the particles, like dry hail, will not reflect very well, so it's also important to remember. So going back to the question, the airborne weather radar is able to detect thunderstorms, of course, with downdrafts by emitting static, not static, turbulence by looking for a frequency shift in combination with pulse flattening. This is exactly the Doppler principle. This is what allows us to detect turbulence. However, remember that clear air turbulence is impossible to detect. The clear air turbulence, the only one that we can actually foresee, are the ones connected to jet streams, because of course, when you see where the jet stream is, then you can anticipate a clear turbulence around that area. However, the weather radars detect it only by measuring the shift in particles and getting that shift in frequency or pulse flattening. So now for question number 5, the gain control knob on an airborne weather radar adjusts so we already discussed it with the help of the previous question. I'll show the image in just a second. So the gain knob adjusts the receiver sensitivity in order to achieve optimum target acquisition. Absolutely. So I'll show you the image right here. On the right side, we have a less sensitive radar with the gain knob set to less sensitive one. And on the right, we have a much higher gain, so a much more sensitive one. So of course, we get the optimum results once you set your gain to an appropriate selection. In most cases, the gain can be left to an auto, which will give you the most optimum results. However, like we just mentioned, if there are a lot of results, like on the left side, you might still need to find the safest path. You can decrease the gain to find the less severe areas. For questions when it comes to weather radar, also remember that all the red cells should in principle be avoided by at least 20 nautical miles, and this should always, if possible, be done upwind. The weather radars and the returns should not be overflown. However, by law, if you are overflying them, 5,000 feet is the minimum. So now going into the last question of the radar, it is very weather radar focused, however, just the radar topic. So for the question number 6, what is the operational purpose for changing the tilt of an on an airborne weather radar system to a higher setting when descending over terrain? So there are two key reasons and functionalities of an airborne weather radar. One, of course, to detect weather. However, second one, in the mapping mode, we can also see the ground returns, and this should not be used to navigate. However, it can increase the situational awareness and help us in some situations. So the weather radar can also be used to see the terrain if tilted downwards. So the main operational purpose of changing the tilt on the airborne weather radar with high setting when descending, it can be to see the ground returns. However, if we do not desire it and we are descending, then of course we need to prevent the clutter that is created by the ground. In that case, you will change the tilt slightly up in order to avoid these returns from the ground, because if you're not meaning to use the mapping mode, then of course you will try to prevent that from happening. So going through the questions here, the higher tilt setting will keep the beam above the aircraft's flight path. It will, absolutely. The higher tilt setting will narrow the beam, allowing the effective detection of cumulonimbus clouds at shorter range, not necessarily. If the beam tilt remains at the setting used during cruise, the scanning range will be reduced and the strength of the reflected signals will be weaker, not necessarily weaker. If the beam tilt remains at the setting used during cruise, the scanning range will be reduced and significant ground clutter may be displayed. And absolutely, this is the correct answer. The examiners want you to remember that the ground clutter is a very real thing that happens very often. So if you do not have an auto tilt, you should tilt it slightly upwards, because otherwise you will not get any credible weather returns, because all you'll see will be the returns from the ground. And this should be the correct answer. So that is it for the radar portion of radio navigation. Thank you so much for joining today. I wish you all the best with your exams, and I hope to see you in the next video. Bye-bye.